Raine?
So, and the last speaker of this session and this show today is Spiering from Trinity College, who will tell us about integrability and quantum chaos in nickel form from the spectral rigidity.
Thank you. Thank you to the organizers for setting up this Scrum show and giving me some time to talk about some work that I did together with Tristan McLaughlin and Raul Pereira. And I'm going to talk about the spectrum of n=4 super Young-Mills theory, both its planar spectrum, there the theory is of course integrable, and I will show how we can see this from the numerical spectrum. And maybe more importantly, I will also talk about the non-planar spectrum, and we will see that this shows features of quantum integrability, of quantum chaos. And so, yeah, this talk is mainly based on this paper here from 2 weeks ago. And there we use several techniques to show exactly this feature, this quantum chaos in the non-planar spectrum. And I will concentrate here on the spectral rigidity. So let me start with just trying to give you an intuition for what the spectral rigidity is. I have 3 spectra here. So this first one is just the spectrum of the quantum harmonic oscillator. The energy levels are evenly distributed. The last one is just a spectrum that I generated randomly I just randomly generated numbers in a certain interval, and I'll refer to this as the Poisson distribution. And then here in the middle, I have a spectrum that is related to random matrix theory. In particular, here I have a spectrum that is related to Gaussian orthogonal ensembles. So this is what you get when you diagonalize a real symmetric random matrix. And this actually is a very important spectrum for physics. Wigner realized that it very well describes the spectrum of, for example, heavy nuclei, but it also models other types of spectra, and people realize that it's spectra of quantum models that have classical chaotic analogs. And so later on, this got a bit shifted. So basically the idea is that quantum chaotic models have spectra that are described by random matrix theory. And similarly, one also found that integral models usually have spectra that are like this random here, like the Poisson distribution. So now what is the spectral rigidity? If I look back at this very first spectrum here, and here there's really no like departure from this uniformity, and this is what I call maximum rigidity. And then at the opposite extreme, I have the Poisson distribution. There is no correlation whatsoever between the energy levels, and this is not rigid. And everything else will lie somewhere in between. So this is a kind of rough understanding for what the spectral rigidity is. Now, for a more quantitative measure, Dyson and Meta came up with this Dyson Meta statistic, delta 3, depending on one argument. And now I'll be talking about scaling dimensions, and usually they are also denoted by delta. But here, really, delta 3 is this Dyson Meta statistic. So now, how is this defined? For this, I just need a tiny bit of notation. So if I have a spectrum, something like this, then I will denote the energy levels by epsilon 1, epsilon 2, up to epsilon n. And then I can build a staircase function. This is just the sum over the Heaviside theta functions, one for each energy level. So if I want to plot this thing, then it would look something like this. I'm going up one step for each energy level. And then I can build the Dyson Meta statistic. This thing here. So inside of these angled brackets, this is just the least square deviation of the staircase function from the best line fitting it, best straight line fitting it. So for example, in this picture here, I would probably have a line here, and then I would just compute the square deviation between those two functions. And then I have those angle brackets. Oh, sorry, I'm actually doing this, computing this deviation in an interval that goes from epsilon 0 to epsilon 0 plus L, and L is the interval length. That also depends here. Like, this is the argument of the statistic. And exactly, yeah. And those angle brackets, they denote the averaging over this epsilon 0. So I'm averaging over the whole spectrum here. So the bigger this L is, the more energy levels I will have here in my interval. And so I look at long range correlations in the spectrum. And if you compute this thing for the 3 spectra that I had in the previous slide, then you find this thing. Down here, the green curve, this is for the uniform distribution. It does some funny things here in the beginning, but they're actually not really important. Important is that for, this is L, this is delta 3. For large L, this roughly becomes constant, and actually 1/12. Then this blue line here is for the Poisson distribution. And this goes linearly in L, L/15. And these are the 2 extremes. So this is no rigidity, this is maximum rigidity, and then everything else would be in between. So for example, the random matrix theory for GOE, it would look like this. So in the beginning, it also goes like L/15, and then it goes like the log of L. So this is a measure for the rigidity, and it actually is, just as a note, related to some other measures like the 2-level correlation function and the spectral form factor. Okay, so now finally, let me come to n=4 super-Young-Mills theory. There we of course have the dilatation operator, and the mixing problem is rather complicated in the planar limit. It's of course simplified due to the integrability. So the SU2 at one loop, the dilatation operator in the SU2 sector maps to the spin chain, XXX spin chain Hamiltonian. But as soon as I go away from this planar limit at finite n, the mixing problem, we don't know how to exactly solve this mixing problem. But what you can do is just take the dilatation operator and put it into Mathematica and solve this problem numerically for certain sectors. And this is kind of what we did. We computed numerical spectra and then computed the spectral rigidity. And those 2 plots here show the spectral rigidity first in the planar limit, so for n=0 and going to infinity, in the SL2 sector and in the SU2 sector. Now I rescale this plot a bit down here. This is actually the GOE curve. So this is again L. And this is here this L/15 for the Poisson distribution. And exactly, yeah. And so those red points, these are the data that we find, and indeed, the data lay on this Poisson expectation very well for SL2, up to maybe 80 here. For SU2, it's not quite so good. The problem here is that the sector is not quite so big. Here we have around 700 states, whereas here we could actually, solving the beta equations in the SL2 sector, we could go, this I think has about 6,500 states. So the statistics is better here, and that's why there's a bit of a deviation here. But also here it works, I don't know, up to length 30. And now if you go to the non-planar case, so now looking at finite n, then this is what we find here. Again, those straight lines, this is Poisson, and the GOE is now this thing, or the random matrix theory is this. And here again, for the SL2 sector and the SU2 sector, we find that the data points now lie on this curve for random matrix theory. And yeah, so this is kind of the conclusion. So we can see from the spectral rigidity that the planar spectrum resembles this Poisson distribution. So this is the sign for integrability. This is how integrability is manifest in the rigidity of the spectrum. And then at the non-planar level, we see that the spectrum, the rigidity of the spectrum is described by random matrix theory. And so this is a signature for quantum chaos. And so in this paper from 2 weeks ago, we looked at the spectral rigidity, but we also looked at the nearest neighbor spacing distribution, and we also looked at the statistics of the eigenvectors, so not the eigenvalues, and also there we found exactly these conclusions. And then the question is, of course, well, this looks very generic. How is there any chance for getting the scaling dimensions still? And of course, the hope is that we can use the integrability of the planar limit to get the non-planar spectrum using perturbation theory. And this is what we did in this paper here from a couple of months ago. Thank you.
Thank you. Now let's mute ourselves, and thanks, Anna. Questions, please?
So these results are at one loop?
This is all the one loop dilatation operator. Yeah. Sorry, I should have.
Yeah. Is there a chance to go beyond that, or is that super hard?
Well, actually in the paper we also look at the two loop dilatation operator. That is also quantum chaotic, so that like the general behavior doesn't really change if I add on the two loop dilatation operator, but also in the integrable limit, this is already quantum chaotic, right? Because I'm only adding the two loop piece. Yeah.
So does it? So it makes it bend down already?
Yeah.
Already
in the integrable case, yeah.
And have you thought about? Have you thought about trying to do some analogous calculation on the string theory side?
Well, yeah, that would be cool to kind of connect with the space-time model, but yeah, we haven't really. But certainly, this is kind of the motivation. Also, like this connection of random matrices and black holes, and yeah, this is certainly very interesting. But we haven't. Well, this was kind of some part of the motivation for this project, but we haven't really connected with it yet. Yeah.
Thanks.
I think like recently there was a paper of Samir who, I don't know, made some connection with black holes even at 3 levels. So I guess with one loop you can just fly. So I don't know whether there are connection or was the paper about, but maybe I'll look at the paper of Samir.
Yeah.
So, can I ask? So I didn't understand. I thought you would apply the rigidity criterion to see whether the model is integrable or the limit is integrable or not. Yes? Was it this?
Well, this is one question you can ask. So can we see the integrability of the, well, okay, the planar limit is of course integrable. The non-planar theory is, I guess, assumed to be non-integrable. And yeah, this is kind of, we see this, like we don't see any traces of integrability in the non-planar spectrum.
Okay, these pictures are convincing, but then you mentioned, answering a question, that if you go to 2 loops, then even in the large n limits, it becomes far from Poisson distribution. Was it so?
Well, if I only add the 2 loop thing, so, but this is not.
Large n, yes?
Yeah, I think this is what we found. Maybe Tristan can say more about this. He looked at this, but
criterion.
But I mean, if I add all the dilatation operators to all loop, then this would be integrable.
Loops are as integrable as. Of course, you have to use the small coupling, yes, because you already have a coupling there. But if you go to small couplings, does it improve? I mean, in comparison to Poisson, does it become closer to Poisson distribution?
Well, yeah, we haven't quite looked at kind of this this transition between like the integrable case and then the chaotic case, but yeah, I guess, yeah. The smaller the coupling, the closer it has to go to the Poisson distribution, yeah.
So one loop is integrable, right? But if you truncate it 2 loops, it's not an integrable system anymore.
No, it's
what
perturbatively integrable. Yes, you
what?
have to work with small coupling. That's true.
Yeah, or just don't consider second loop.
Yeah.
Ask a question.
Okay, I'm a bit lost. Yes.
Why do the red dots sort of deviate from the blue line at the large L?
Yeah, that's a very interesting question. So, of course, if the spectrum was completely random, for example, now here in the integrable case, then the dots would follow this blue line until kind of the end of the spectrum. Like if I run over the spectrum, then of course it will deviate. But certainly at L being 80, we're not running over the spectrum if I have 6,500 states. So this is not this. There's really it's assumed that there is some physics behind this. Actually, this was already observed by Barry, I think, in the 70s, who actually could make the connection between classical integrability and this linear behavior of the spectral rigidity. I think on the basis of the action angle variables, he really computed this alpha 15, and he also realized that this only works up to some L max, and from there on it's supposed to saturate. So this is in the classical case. I haven't seen anyone make this connection clear for the quantum integral case, but so I kind of assume that also here this is some sort of non-universal thing happening. Yeah, and this Lmax, it kind of depends on the degrees of freedom that I have in the system. And so also, if we look at other sectors here that have smaller Hilbert spaces or bigger Hilbert spaces, this will change the Lmax that we find. But in the non-planar case, actually also there, Barry says that it should saturate. Here we find actually that it goes up. So this is probably more of a statistical problem.
Thanks.
So we should move to the discussion mode, but there is no.
Oh, we already is there. We should wait on one more time.
So one difference, I just let's thank the speaker and I turn off the recording.